Hello. So now that we're done with sequence networks, so I basically introduced you into four-test theorem, and then how are we going to use that theorem to analyze unsymmetrical faults. So I think we're now ready to look into shunt faults. So for now, we'll discuss shunt faults, and then later on I think I'll try to do series faults, but yeah, well, the idea is that for shunt faults we are analyzing short circuit faults. For series faults, we'll be analyzing open circuit faults. Okay, so for shunt faults, we actually have four different shunt faults. I'll discuss that to you later. We'll be considering this system. This is basically the same system that I'm using on my other fault analysis videos. This is a two-bus system with a generator supplying a motor. So for this particular example, we'll assume that your generator is Y grounded, your motor is Y grounded. We'll drop the load currents. So if you're not familiar with what I'm talking about, I think you may want to check the other video on Thevenin equivalent circuit. Okay, so we'll assume a fault at bus 2. So it's at the terminal. So that's the fault point, and then the network sequence that we'll be assuming is ABC. So it's ABC sequence: A leading B, B leading C, C leading A, and basically that's the cycle. So I took the liberty of assigning my impedances to form the impedance diagram. As you can see, every element has three impedances to represent the three impedance networks. So you have the positive sequence, the negative sequence, and the zero sequence network. So each impedance here is given in that order. So for the generator, the positive sequence impedance is 0.1, 0.1 for the negative sequence, 0.05 for the zero sequence. That's so that's why it's given in sets of three. Okay, so what I want to show you is the different representations on three-phase fault: single line to ground fault, double line to ground fault, line to line, and line to line fault. I think I did line to line fault first before double line to ground. Yeah. But yeah, anyways, okay, so let's talk about three-phase fault first. So this is the only symmetrical fault here. The idea is that when the fault happens, your system is still balanced. I discussed this before. So all of your lines are shorted. All of these three lines are shorted with each other. It can be grounded, it can be ungrounded. It doesn't really matter, because if the system is balanced and it experiences a balanced fault, therefore it's asymmetrical fault. Therefore, its fault current, its fault current going to the neutral is still zero. So it doesn't really matter. I've shown the solution here for this particular example on symmetrical faults in my previous video, I think. So if you can still remember what we did before, I think I can find it here. This one. What we did before is we represent it into two different superposition. Again, as I have said before, I'll be dropping the first superposition, so we're left with this one for the solution, and this is just your Thevenin equivalent circuit for the network at the fault point to the neutral. So yeah, as you can see, if we have this Thevenin equivalent circuit, then we're done with the solution, and it's basically your Thevenin equivalent circuit. It's basically this Thevenin equivalent circuit. So as I have said, if you have this Thevenin equivalent circuit here, you're done with the solution. So you don't really need the negative sequence and the zero sequence anymore. So for three-phase faults, you don't actually need the zero sequence and the negative sequence. So your fault current will actually be just your positive sequence fault current, as I have shown here. As you can see, you won't have a zero sequence and a negative sequence fault current here, because these two networks are open circuits. So yeah, you may represent it this way, but the values are still 0. Therefore, you just have a closed loop here at the positive sequence. The positive sequence, this one. Now, if your fault, if your system is experiencing a fault impedance, if the fault introduced a fault impedance into the system, then you may incorporate that fault impedance here in the network. In the expanded form, that's just basically this one. Okay, so this expanded form actually tells me a lot about the system. Excuse me. It tells me a lot about the system. As you can see, again, my negative sequence and zero sequence are zeros, so they don't have any value. If I compute for the fault current, it's basically the sum of the three. So it's the positive sequence, the negative sequence, and the zero sequence. And take note, this is 0. These two are zeros. So you're just left with this one. Now, why do I want the expanded form? Because it can tell me the information of the currents going coming from the different components. In this case, from the generator and from the motor. Those are the two currents from the two current sources. And it tells me the information about those two currents for different symmetrical components. It just so happened that for the negative sequence and the zero sequence, the values for the IG and IM are 0 because this is 0. The total current here is 0. So, and it's the same for the zero sequence. The currents here from the generator and the motor is 0 because the total current here is just 0. But yeah, if I know the currents from the generator and the motor for the three symmetrical components, then I can compute for the net contribution of the current. Now take note, as you can see here, if you'll notice, I am just computing for IAF. IAF, yeah. All of these are in terms of line currents on A. So why is that? Because I use this voltage as my reference, and that is on AB. So yeah, that is on phase A. Yeah, that is on phase A. Sorry. Now, how do I get the currents at IBF and ICF? Well, this is a three-phase fault, so it is balanced. So you can just displace the IAF by positive or negative 120 degrees, depending on the phase sequence. Well, in this case, it's what do you call this? Positive sequence. So it's negative 124 IB, positive 124 IC. Okay, so yeah, but that's just it. Okay, now let's proceed to unsymmetrical faults. So that's the only symmetrical fault here. Now when dealing with unsymmetrical faults, it gets a bit more fun because you'll now see how the symmetrical components affects the fault current. Okay. So let's say that I experienced a single line to ground fault of line A. So the idea is that I have a three-phase system, 3 lines between buses 1 and 2, and then on bus 2 I experienced a fault that shorts line A to the ground. So as shown in this diagram. So as you can see, I have a fault current IA here. Okay. So I have the 3 sequence networks here. This is my positive sequence, the negative sequence, and the zero sequence. Now, these 3 sequence networks in a single line to ground fault that occurs at line A, take note, that is at line A. That is important. That is at line A. The 3 sequence networks, for a single line to ground fault of line A, the 3 sequence networks are connected in this way, such that your IAF, IA1, IA2, and IA0 are equal. They are basically in series. And these 3 sequence networks is in series with a 3ZG. What is this 3ZG? Again, if your fault introduced an impedance, if the event of fault introduced a fault impedance into the system, then that is your then you introduce that into the network. So this 3ZG is this ZG here, or yeah, I think I can use ZF. It's basically your fault impedance. I just use ZG because it's connected to the ground, so it's basically a grounding impedance. Okay, so that's the grounding impedance of the fault or your fault impedance. Okay, so you have these three networks here in series with 3ZG. Well, all of them are in series. Okay, so that's how you represent your single line to ground fault. The expanded form of that is this one. So it's you basically have the ZTH here. This is your ZTH. 0.2 plus 0.1 parallel 0.1. You have the ZTH here for the negative sequence, and this ZTH here for the zero sequence. It's 0.05 plus 0.1 parallel 0.05. Okay, and then from here you can get IA1. This is IA1 here, so that's basically this current here. IA2 is this current here. IA0 is this current here. Okay. So yeah, it's basically the same analysis, you just have a different representation. So to get the fault current IAF, you just sum the different symmetrical components, IA1, IA2, and IA0. You can also get IG and IM for, again, take note for line A. Because all of these symmetrical networks tells you how to get the symmetrical networks for line A. And it's line A only. So how do we compute for it's for line A. Yeah, yun lang muna. Okay. Now how about IBF and ICF, the fault current at B and at C? Well, technically, the single line to ground fault occurs at line A. Therefore, you don't actually have a fault current on B and on C. You can verify that using your A matrix, if you can still remember. I have this on my, I think it's on another video about Fortesque theorem. So yeah, as you can see, we are just solving for the currents right now, but this method is also applicable for the voltages. I guess for the voltages, what you want is this VA. This is basically the voltage A. I think I'll just use this. This is VA1 from the fault point to the neutral. VA2 from the fault point to the neutral. And VA0 from the fault point to the neutral. It's the same for three-phase fault. So yeah, you have the three symmetrical components for the voltages. So you get the VAF using the sum of those three. Okay, that's for single line to ground. I have line-to-line fault. So this is basically your line-to-line fault. Your line-to-line fault, take note, this is the solution for the line-to-line fault between lines B and C. Take note, this is for lines B and C. So what happens here is you have a tree line between 1 and 2. Your B and C are shorted. So I guess it's easy to say that IBF is just the negative of ICF. They are basically opposing each other. They have the same magnitude but opposite in direction. So the diagram for that fault is you have the three sequence networks here, and then basically your fault your what's this, your zero sequence network is not connected to the positive and negative networks. That's why your IA0 is basically 0. That's the value of IA0. And your IA1 is basically negative of IA2. Now, these two, these two networks, the positive sequence and the negative sequence, are in series with your fault impedance. If if the fault introduce fault impedance into the system. So I guess the fault impedance is when you have a shorting impedance between lines B and C. Okay, I haven't shown the expanded form here because it's just the same as this one. You just modify the connections. Okay, so I guess for the line-to-line fault, you just connect these two, and then you introduce ZF here, and then yeah, you leave this open. Okay, so that's line-to-line fault. Now for the last fault, this is a double line to ground fault between lines B and C. Take note, this is between lines B and C. So what we've done is single line to ground fault on A, double line to line fault on between B and C, and double line to ground fault between B and C. So the idea is that basically what you have is two lines that are grounded. Okay, so from here you have IBF, you have ICF. You can no longer say that IBF is negative of ICF, I think. Yeah. Then we may experience two different fault impedances. The fault impedance on the line and a grounding fault impedance here. So that's ZG. That's why in the sequence networks, as you can see, this is basically your sequence network. This one. I'll zoom this out. So this is your sequence networks, 3 sequence networks. And then for the fault impedances, if there is a fault impedance, you have ZF in series with positive sequence, ZF in series with negative sequence, and ZF plus 3ZG in series with the zero sequence. Okay, and all of these are in parallel. So yeah, you just solve for IA1, IA2, and IA0, and then you get the IAF. Well, the IAF here is actually 0. As you can see, you don't have a shorted current on line A. So sir, why are we solving for IAF if we don't have an IAF here? Well, we'll be using that IAF. We'll be using these values IA1, IA2, and IA0 to get IBF and ICF, because we can relate IA1F. We can relate IBF to get with IA1F, IA2F, and IA0F using your A matrix here. So basically the idea is you want to use this every time. So I'll get the 3 fault currents by just solving for the currents on IA1, IA2, and IA0, because that is possible, because you know that the positive sequence, negative sequence, and zero sequence are balanced systems. So you actually have a value. You can actually use these values to get IB1, IC1, IB2, IC2, and IB0 and IC0. So yeah, so that's basically it. That is what your A matrix is doing here. Okay. What more can I say? Okay. So take note again. I'll reiterate that this is for line A, or single line to ground fault on line A. Line to line fault between B and C, and then a double line to ground fault between B and C. So sir, what will happen if the double line to ground fault happens between, let's say, C and A, or A and B? So if that happens, then we'll do something with the solution. We'll tweak the solution somewhere, but I'll do that in another video, I guess, because it's it will just bombard you with a lot of information. So I guess it's harder to digest that in a single video. So yeah, I guess that's it for the representations of shunt faults.